Hello all, I'm going to be looking at the reactivity series today. It's a fairly straightforward one, very practical part of life. Doesn't matter whether you're particularly interested in science or not, this will feature in all your life. Some of you will be sitting there with an iPhone and you'll probably notice that some of it's made of metal. And now that metal doesn't just come out of the ground like you're holding it there. It has to be mined out of the ground, usually as an ore, which means it's mixed in with other things. It has to be separated out. And what we want to do is look at some of the processes over the next few lessons on how we separate things out. So this will apply to anybody who's thinking about recycling, reusing, because we want to try and avoid digging things out of the ground unnecessarily. And you need to have a little bit of context of how much is involved when we do have to take it out of the ground as a raw material. So normally, if we're in a classroom, I'd be doing this little exercise, but we'll skip through it because this is just about making sure we can link what we're doing in these few lessons back to things you've done previously. But I'll cover on that in a little bit more detail. So, reactivity series, in your books, so if I just give myself a pen here, what I would expect you to do at this stage, and you'll see me do this plenty of times, is to draw this circle. I won't draw it around because it's drawn nicely for me. 2 circles and write the word reactivity series in here. Now, we're going to add some key words. So I've already talked about a few in here. So words like ore. So coming out of the ground is ore. We're talking about certain metals. Okay, these are all going to be about metals. And we might list some of them. So some of the common metals. So I talked about your iPhones earlier, so aluminium fits in here, if I can spell it. We have things like nickel. Most of you know the battery, and the battery uses a metal called lithium. And we're going to keep adding to this, because if we make this properly at this stage of learning these 3 lessons, this is everything you need, all the key terms and key words. So when you make your little revision document at the end of the topic, this is your go-to place. This is where you're going to pick up all those keywords that we want you to use when you're answering a question. Okay, so the purpose of this lesson is we want to have a look at relative reactivity. So this word here, relative reactivity. Now, relative has meanings elsewhere, like if your brother and sisters are relatives to you. But in this instance, relative just means the difference. So if I write that in, the difference between 2 things. Doesn't matter what the 2 things is. We're not really care what they are. We just want to look at the difference between them. And we have a look at different metals react in different ways, which we've seen in the classroom before. So I'm not teaching you anything you don't know. I'm just going to put it in a context that we can use. And we're going to have a look at this term over here, displacement. Now, we use displacement for loads of things in science. But in this instance, displacement means I'm going to take one thing and I'm going to replace it with another. I'm going to displace it with another thing. And we'll discuss that in more detail as we go. Okay, so this is the reactivity series. And I'd like you to pause the video here, please, and copy this into your books. Okay. And that is the reactivity series. I'm going to use that quite a few times. So make sure you pause the video, write that down, and then join back in with it. Okay, so hopefully you've drawn that in, and it just simply tells us the most reactive, sorry, try and draw over things, to the least reactive. So potassium at the top, really, really reactive. Put potassium in water, it spits, it bubbles, it sometimes goes bang. Compared to gold, which pretty much doesn't react with anything, and you can find gold in the ground. Pull it straight out of the ground because it won't react with anything in the ground. Okay, so this is just an order of how reactive things are. Okay, so we're going to look at which metals are going to have an effect, and we're going to start off with copper down here. So Mr. Copper and Miss Sulfate, and they've got a nice. So copper sulfate, something you've come across before, hopefully. So copper sulfate has a nice imaginary bond between. And I've drawn the arrow to create our imaginary bond. But along comes Mr. Zinc. And Mr. Zinc is more reactive than Mr. Copper. So zinc is actually going to displace copper. So copper is going to get thrown out. So now we're going to have a zinc and sulfate, or zinc sulfate, which is great. but who needs zinc sulfate? Well, the answer is we don't. But what got removed was copper, so just copper on its own. Now, copper on its own is quite expensive. It's pure copper. It's very valuable, useful for all sorts of electronic equipment. So we've used our displacement procedure to remove or displace out the copper that we want. And we've used zinc to do that because zinc is more reactive. If I tried to add silver here, the copper is more reactive, so the silver wouldn't have done anything. So using zinc is a good way of extracting copper. So I think we're going to get a further example of that here. So copper sulfate, if I add the zinc, I'm going to end up with zinc sulfate plus copper. Now you'll notice here, we're going to have copper sulfate plus zinc goes to zinc sulfate plus copper. I'm not going to balance that up, but the point is to show you that this is the word version. This is our equation version. Oh, lost that. So if I ask you to put it in the equation form, this is the form I'd like. Word form like this. I'm not going to expect you to draw pictures of people. Okay, but if I do it the other way, so zinc sulfate plus copper, well, we've already discussed this. We know that copper isn't as reactive as zinc, so nothing will happen. Zinc sulfate will just stay as zinc sulfate. Okay, so some things you do in class in this instance is you do this procedure where we'd give you, well, we wouldn't give you any of these. They're too reactive for you to use, but you might use some of these. And we might ask you to add them with water. We might ask you to add them with steam. Now, obviously, steam has its own inherent risks, and they will react the hotter it is. If you add more energy into the system, the reaction rate increases. Hence why steam is more reactive, going to be more in effect than cold water. And some of the things you might see, obviously, up here, if we add acid to things, we actually get an even stronger reaction than water. But that wouldn't probably surprise you. And this is another great keyword to add on, or positive ions, cations, okay, which we're going to use a lot when we're talking about our bonds and why bonds form and how we can extract things from soluble solutions, etc. So this is going to link really strongly over this side to lessons as we progress. So there's loads of keywords here. So if you go back to your circle map, with reactivity series in the center, you've got lots, pause the video, you've got lots and lots of keywords that should be in there. You should have reaction, you should have water, no we won't do water, we'll have forming hydrogens and metal oxides, make sure you add those in. We definitely want to include hydrogen, we've got hydrogen there, salt solution, definitely involve cations, positive ions for sure. I mean, there's loads and loads of keywords on that page that should all end up in your circle map. Okay, so this is where I'm going to get you to pause the video a lot. So here are 4 questions that you would have to answer on one question, if you like. It's 4 parts to it, but I'm going to walk you through it. So I'm going to model what I would do. So I've got, will a displacement reaction occur if I add magnesium and iron chloride? Well, the first thing I want to do, I'm going to circle, that's a line. I'm going to put a line under my 2 metals, and I'm going to find them on here. So I've got iron here, and I've got magnesium here. Now, straight away, I can see that magnesium is more reactive than iron. Okay, so check the reactivity series. Is magnesium above iron? Yes, it is above iron. Will magnesium take iron's place and make magnesium chloride? Well, what do we think? If you're not sure, well, if it's more reactive, it should probably take its place. Okay, there we go. So we write the word equation for this reaction. So the word equation, magnesium plus iron chloride, so that was our question from up here. And we need to put down what, we use this arrow, we don't use an equal sign. Arrow turns magnesium chloride and iron separately. So we've split up the iron chloride, and now we've got magnesium chloride and iron. Write a symbol equation. So iron chloride is FeCl3, so Fe and Cl3 for the chloride. And remember how we wrote that out in the last slide. It should look like Mg plus FeCl3 goes to magnesium chloride plus iron. And they've balanced that out for us. Okay, so that's the kind of thing we're going to expect you to get to. It doesn't happen straight away. So you'll have this video to go back to check if you want to practice them. But what I'd like you to do is take what you've just seen there and try and use it in the slide. Okay, so displacement, these are just yes and no. Will a reaction occur? So I'd like you to pause the video. You need a yes, no, yes, no, yes, no for all 5 questions. So by all 5 questions, I mean, I've lost my pen. There it is. So question there, 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 and there, and there. So I need 5 answers from you. And come back and press play when you've had a guess on all 5 and see if you're right. Mark them. Okay, so if you're back with us, here we go. Oh, they're going to pop up everywhere. That's just to put us on our toes. There we go. So sodium will react with iron chloride. Sodium's far more reactive. It's number 2 on the table. Magnesium, potassium, I would think not. Potassium's the most reactive. Magnesium's, well, 4th down in this list. Iron and calcium, no, because iron is lower. Zinc and copper, yes, because the zinc is higher. And this example we used earlier. Copper and silver nitrate, yep, absolutely. And for a bonus point, what would be left over from the last one? You'd end up with silver. So you get silver on its own. Silver is quite valuable. Okay, so this is the last bit of the lesson. So what I'd like you to do is write these down and fill them in with a different coloured pen if necessary, and then mark them. So pause the video, and I'm going to stop talking for about 5 seconds while you pause it, and I'm going to come back and you can check your answers off. So pause it now. Okay, welcome back. So here is the answer checking. So magnesium nitrate, copper sulfate, zinc, copper, and for the silver section, so well done if you've completed the bronze section, and if you got onto the silver section and go with these, well done. Word equations for the following reactions: zinc sulfate and copper, magnesium nitrate and silver, potassium nitrate and zinc, iron sulfate and gold. And for the gold area, for those of you who can go to this is the skill set that we really want you to all have by the end, if you can actually write out the balanced symbol equations. And this is what they would look like. So well done if you got those. Now, if you've got any questions, please make sure you ask. You've got my email address, and you can also meet up in the live lessons. Please, please, please go back to your circle map now and add in all the key words from the lesson. There are loads, and we're going to use them lots and lots over the next few lessons.